Okay, in this problem, I want to find the moment of inertia of this cross-sectional area of a beam about the centroidal axis that is defined as x prime right here. Okay, so what I'll do is I'm going to break this up into three simple shapes. Circle on the bottom, I'll call 1. Circle on the top, I'll call 2. And then this rectangle that I'll call 3. Okay, and what I need to do is I need to find the moment of inertia of each piece of this, each component of this, about that x prime axis. And the way I do that is using your parallel axis theorem, where you take that centroidal moment of inertia of the shape, okay, and you add a times the distance between the two axes squared. So let's go ahead and do this for number 1. We'll find number 1 about the x prime axis. Now, I'm finding, and I'm going to look up the moment of inertia about this axis right here. Okay, that axis right there, okay, has I looked that up in the back of the book. The moment of inertia about that axis is 1/4 pi r to the fourth, where r is going to be 25 millimeters to the fourth. So that's the moment of inertia about that centroidal axis right there. Okay, what I'm going to do is then I'm going to add the area of this, which is going to be pi r squared, which is pi times 25 squared, times the distance between that axis that goes through the center of the circle up to the y prime axis. I'm sorry, the x prime axis, which is right there. Okay, now this distance right here is 25. That's the radius of the circle. Okay, so the distance right here is actually going to be 104.3 minus 25. That's the distance that I need. That's actually going to be 79.3. That's what I put in right here, 79.3 squared. Again, it's the distance between the center of my circle and the axis that I'm finding the moment of inertia about. And when I do that, I get 12.7 times 10 to the 6th, so 12.7 million millimeters to the fourth. Okay, I'll do something very similar for that top guy right there. Okay, so this one's going to be 1/4 pi, and then this will be 17.5 to the fourth. That's the radius of that top circle. And then pi r squared, same uh, radius, 17.5. Now I need the distance. Again, that's the moment of inertia about that centroidal axis. So I'm looking for this distance right here. That's the d that I'm looking for. Okay. What I know is, I'll do it this way. This distance is going to be 217.5. And I get that from the 50 diameter plus the 150 of the rectangle plus the radius of 17.5. So that's 217.5, which means that the distance that I'm looking for here is 217.5 minus that 104.3 given right there, which gives me 113.2, which is what I put in right here squared. That's the distance between the axis of interest and the centroidal axis of my circle. So you got to find that distance, square it, add that there, which gives me the moment of inertia of that circle about x prime equal to 12.4 times 10 to the 6. And you'll notice that these have an equivalent moment of inertia about the axis. Even though the 50 is obviously bigger than the 35. The fact that 35 is further away from that x-axis kind of balances out that size difference that we get there. So those moment of inertias are pretty similar to each other about the centroidal axis that I've got there. Okay. Now we got to do the same thing with the rectangle. Okay. So for a rectangle, it's 1/12 base times height cubed. When I look that up in the back of the book, that's for the moment of inertia about its centroid, which we'll get to in just a second. So the width on this is 15. The height on it is 150. So 1/12 BH cubed. Okay, now the area of this is just 15 times 150. And again, now I need the distance between that x prime axis and, say, the center axis right here. Okay? Now, that center axis, I'll go right here, goes up 50 and then up another 75 because the center of that rectangle is half of the 150. So I go 50, this is going to be 125. That means that distance between the two, it's getting a little dicey in here, okay, is going to be 125 minus the 104.3. Okay, so that is, what would that be? I don't actually have it, so I'll just throw it in right here. 125 minus 104.3 squared. Okay, so again, same idea here. You take the moment of inertia about the middle of the rectangle. You look that up in the back of the book, 1/12 bh cubed. Take that, add it to the area, which is base times height, times the distance between that middle of the rectangle and the x prime axis, which is, 20.7, I think, here. Anyway, when I do that, I get 5.18 times 10 to the 6th millimeters cubed. So you can see here that actually those circles are contributing more to the moment of inertia than the rectangle itself, even though the rectangle likely has a bigger area than the circles, but the fact that those circles are so far away from the axis give them a greater moment of inertia. Now all I need to do is add those guys up to find the total. So I get 112.7 plus 12.4, excuse me, plus 5.18. And again, these are all times 10 to the 6th. That gives me a moment of inertia of 30.2 times 10 to the 6th millimeters to the 4th. So again, break it up into simple shapes, use the parallel axis theorem to find the moment of inertia of each piece about its axis, and then simply add them all together.